Good evening, ladies and gentlemen. My name is Dr. Pietro Tricoli. I'm a reader in Power Electronic Systems from the University of Birmingham. I'm delighted to give you today a talk on railways in the era of decarbonisation and the challenges of traction power systems. So, electric railways are changing rapidly, and this is also due to the rapid change of the public grid feeding the electric trains. This is because we are moving towards a higher proportion of electricity provided by renewable power. And at the same time, we are also seeing a larger number of electric lines being built around the world to phase out diesel train. However, there is a big question: is electrification always possible, and is always the right thing to do to decarbonize transport? So similarly, whatever is the primary source of power, how railways can reduce the energy consumption and then the environmental impact. And what are the most promising technologies that could help that? And then talk about energy storage like batteries or fuel cells. And finally, what railway can do also to be competitive in helping the grid and then tackling what is happening into the grid market, for example, providing services or helping the grid and mitigating the current issues facing the grid. So the speech will start with some recent research work on rail electrification systems, so the fixed infrastructure, and then it will move on onto onboard technologies to reduce the environmental impact of railway, especially independently power train. Many electric railways, they are electrified with DC power or AC power, albeit most of the new line will be electrified with AC. And the traditional electrification system is a single phase AC, which has transformer feeder stations. The transformer feeder stations are single phase transformer connected to the three-phase grid. And the imbalance of the load, of the traction load, require the connection to transmission systems at high voltages. And this is usually an expensive kind of solution. And similarly, due to the different phases feeding the railway to balance the grid, results in the need of introducing neutral sections that are electrically isolating the different sections of the railway. And this is also causing an additional problem, because when the train is moving through the three phases, it needs to open and close its circuit breaker to avoid short-circuiting the different sections. And finally, as transformers are passive, they cannot actively control the voltage, so they have a regulation effect, and this is also causing additional power losses onto the rail electrification lines. This is an example of an existing traction power supply. So this is the Sellindge substation in HS1, is a high-speed line connecting London to Paris and Brussels. And this substation is feeding a large area around the railway, and has a 400 kV line input. And two of these transformers are dedicated for feeding the railway line, which is in here. And as you can see, there is this area on the left-hand side, and this is an SVC. Is a static VAR compensator. So it's a big power converter that is compensating for the imbalance of the rail traction load, as well as the imbalance of other load in the area, which is quite big, because it has a capability of up to 168 megavolt ampere reactive. And then the natural question is, rather than introducing the imbalance, for example, from using a railway traction load, single phase railway traction load, and then compensating for that using these big compensating stations, why we don't directly compensate or draw a balance power from the grid? And to answer that question, over the recent year, there's been a lot of work into developing a traction power substation using static frequency converter. And this slide shows the basic concept. So this converter use a back-to-back converter module, which is converting three-phase power connected to the main public grid into DC power, and then DC power back into single-phase power. Which is connected to the electrification line. Due to the controlled nature of the converter, we can then avoid the neutral section because we can avoid the circulation of power between the traction substation, and then each train is fed by two or more substations, and that enable a larger spacing between the feeder stations. Similarly, the controlled nature of the converter enables to draw balance current from the grid, and therefore there is a possibility of connecting to weaker grid or even to grids at lower voltage, than saving on the connection costs. There are a number of converter topologies for static frequency converter, which are then reported here in this slide. So all of them are, to some extent, multi-level topologies and modular topologies to reach the typical power of these substations, which range anywhere between 10 to 20 MVA. And in the first topology, it's called the back-to-back topology. We have two sections in parallel in here with two three-phase, three-level neutral point clamped active front-end converter. And these are connected via this three-winding transformer with a delta star connection to reduce the harmonic on the incomer. And then there is a central DC link, which is common of the two converters in here. And then there is a number of modules, single phase module generating single phase AC power, and a transformer here, which is connected in parallel connection or independent connection on the primary side and series connection on the secondary side to obtain the 25 kV. Also, we can note that there is this filter in here at 100 Hertz, which is a resonant tank, which is helping to limit the oscillation across these capacitors. Obviously, this filter is tuned at 100 Hertz for 50 Hertz railway, and it will be 33 Hertz for 16 and 67 Hertz railway. The topology is similar to these ones, albeit with some differences, is the multiple DC link topologies, and in this case each back-to-back converter is separated from each other, and they are parallel connected on the three-phase side, and they are series connected on the single-phase side. The advantage of this topology is that the voltage on the single-phase side before the transformer can be increased by adding more modules. And also the waveform here is sort of a multi-level waveform. So by adding a sufficient number of modules, it's even possible to remove completely the single-phase transformer at the output in here. The last topology, which also has been explored for 50 Hertz railway, is a modular multi-level topology, which is based on the classical MMC topologies. However, as the input and the output frequency are the same, we cannot obtain a direct conversion of AC power into AC power, but we need to have two separate sections. So we will have a three-phase MMC, which is generating a DC voltage here, which is approximately as a value of around 50 kV. And then there is a single phase section, which is then reinverting that DC power back into single phase AC. This topology is called also transformerless, because by adding a sufficient number of modules on the converter, we can eliminate the need of a transformer on the output side. So this will also help to increase the efficiency compared to the other topology. In terms of quality of the waveforms, the three converters, they have a slightly different quality. And in this simulation, we have compared the voltages and the related current of these three topologies. Obviously, the better quality is achieved by the MMC, where we need around 11 modules to obtain the 25 kV. And then the multiple DC link is, the second best, and the back-to-back converter is slightly worse than the other, but is still quite good. So there are obviously advantages and disadvantages for the various topologies, and they have been used, at least the first two quite widely for 16 Hz and 50 Hz railway, while the MMC has been used mainly for 16 Hz railway, due to the advantage of having a conversion in a single step. For a 50 Hz railway, the advantage is slightly reduced because of the need of this double stage conversion. Advantage of having a traction power substation with converter is the independent control of the active and reactive power. So in this simulation, I have analyzed the current drawn by the converter on the three-phase side with a step change in the load. Before 1.5 seconds, there is a very, very low power. So the converter operates at no load on the railway side, and then there is a step change on the output side. And as you can see, the power factor is maintained equal to unity, respectively if it is a high load or low load. And another advantage is the possibility of controlling independently the active and reactive power, which is shown in the slide here on the right-hand side. And this is helpful, obviously, to help the grid, because this converter could also sustain the voltage if needed, and then can operate also as a compensator if needed, which is a great advantage compared to transformer substation. The other thing important is the reduction of fault current because of the controlled nature of the converter. In this slide, I have presented what happens in case of a short circuit at just the output of the bus bars of the converter. And there you can see the current initially is going up and shoot up quite quickly, but then the converter control enables to reduce the current to a value which is not much bigger than the nominal current, in this case just 50% bigger, and that helps reduce the complexity of the switch gears compared to a traditional railway. Then moving on to a different subject, the rail electrification, as I said, we need in the future to have a better interconnection with the public grid. And in this example here, I'm going to show you some of the research which is around the usage of smart soft open point for electric railway. So in this configuration, the rail electrification is fed from the traction substation. However, there are no other connection with other nodes of the rail of the public grid, so the non-rail grid. And the main idea is to introduce a converter which can transfer power in a controlled way between the rail electrification and the other node of the grid. And this could be particularly useful in this other node. There is some renewables, or there are some EVs where the rail electrification can support the feeding of these EV loads, or could benefit from the power generated by PVs. And one critical element to achieve this is the usage of energy storage, because we could have a direct feeding of the rail electrification, but in that case, it will not probably be the best option, because that would only increase the length of the transmission distance. But instead, what we could do is to inject into the public grid only the braking energy obtained from regenerative braking of the train. So all the energy that normally is not recovered within the rail network is going to be sent through the smart soft open point to this network. And this will then increase the efficiency, because we are increasing the amount of energy that is recuperated. So this, in this slide, is an example of how the smart SOP can be connected. So there will be a converter here connected to the rail. In this example is with the DC rail, which is actually the type of railway like underground or suburban railway most likely to be present close to urban center or rural center. And so this converter is then connected to the rail, and then is responsible for transferring the braking energy of the train back to the grid. And then the battery or energy storage is also connected via converter, and the amount of energy that is transferred from the rail to the battery or from the rail to the grid is controlled by the presence or not of the regenerative braking energy. If the battery is not receptive, or then there is also a possibility of sending the power directly to the local grid, where there might be not just local loads, but also renewable energy and EVs. And in case of an excess of power generated by renewable energy, in the current situation without the SOP, all the excess power would need to be injected to the grid itself and sent to large distances, creating additional losses. Instead, with the SOP, it is possible to store that extra energy into the battery and then reuse it on a later time. A different configuration of the SOP is instead if we have a larger scale system where we can inject power and balance power between different supply, high voltage supply of the DSO. So in this case, the main role of the SOP is to balance the power between these two feeders, and then contribute to the balancing of the DSO network. So it's a different function, because before it was mainly for the local load on the low voltage network, and in this case is for the DSO at the medium voltage network. In this simulation, it is shown what is the effect of connecting the SOP to the traction power network. So this is done using our multi-train simulator. So the figure on the left is showing what is the power consumption of the traction substation without the SOP. And the one on the right is showing what happens when we add an SOP on substation number 4. And it is clear that we have some time when we have some regenerative braking power. And then with the analysis of the operation of the network over a long time, we can see that the amount of regenerative braking energy is actually increasing by around 5 megawatt hour in a day. And the energy recuperation then increases from around 91% to 99%. Then in our study, we went a little bit more in depth into understanding how, what is the best position of the SOP. So we have looked at a sample line with 11 substation in here, and then studying the power flow using the train simulator. It is possible to obtain the substation where the regenerative braking energy is the maximum level, compared to the case where there are no SOPs and the recuperation is around 90%. And we also have done this with the adding a second SOP to the network, and it is possible to see that if we have just two SOPs, the braking efficiency reaches nearly 100%. So generally speaking, we can conclude that there is no need to have SOPs at all the traction substations, but it is enough to have around two of them on each rail line to obtain a recuperation of nearly 100% of the regenerative braking power. And this slide shows what happens on the low voltage grid. So we have simulated the SOP connected to the low voltage grid in configuration number 1. So connected to a residential network. And we have assumed also that on the network there are a number of solar photovoltaic producing power according to typical power generation, which is changing during the winter, during the summer, and changing during the day. And we have done a number of analyses to see what happens to the power consumption at that local node. Well, the results are shown in here, and as you can see, the braking efficiency increased considerably by adding the SOP, and this is actually in agreement with what we've seen before. But most importantly, we have a much higher local consumption of the renewable energy because of the battery. So when we are looking at what is the energy consumption from the grid transformer, we can see that there is a significant reduction of the energy needed from the grid transformer, which means that the local loads, as well as the local renewables, together with the battery and the input from the railway, are able to operate almost independently. And as you can see here, you can see that the consumption reduces from 6 megawatt hour to nearly zero. And on the left-hand side, we can also see what happens to the energy storage. So during the morning, there is a significant train demand. So the energy during the morning is here. This is the time. The state of charge of the battery will reduce because there is a consumption also from the local load. And then during the afternoon, when there is a reduction of consumption, then all the braking energy from the train, they continue during the day, they will replenish the energy storage. And then during the evening, when then the people will come back home, the energy storage will then go, the state of charge will then go down again, also because during the evening there will be less trains. And during the night is the only time where there is a little bit of top up from the power grid, which is responsible for this 0.34 megawatt hour, which is not basically a problem because during the nighttime the grid is less loaded. So all these controls and all these control strategies are going to be tested first into a lab, and this is the batteries as well as the smart SOP currently under testing in the University of Newcastle. And then in the last phase of this project, all the SOP will be then shipped to Metro de Madrid, and it will be tested on line 9. Talking about rail electrification, and then talking about the usage of static frequency converter, one of the things that is currently under exploration is based on this consideration. So if I want to replace a transformer with a static frequency converter, why do I need to use 50 Hz as the output? Well, the answer is I don't, because the 50 Hz makes sense only if I have use a transformer, which is a chip component, and the grid is 50 Hz, and that's why I use 50 Hz. So there is quite a lot of research into looking at different frequencies of supplying the rail traction network. And one of these frequencies is actually using 0 Hz, so using a DC power supply. And there are a lot of research on MVDC grids, and there is also some research on MVDC traction power grids. And one of the main reasons to do that is because, of course, they will be more suitable for a high penetration of renewable sources, for a direct feeding of the traction power network from renewables, but also they will have the advantage of operating like DC networks. So there will be no need of neutral section. They could be connected to distribution network operating at lower voltages, and potentially they could also have a bidirectional converter to export renewable power back to the public grid. Obviously, problems with this kind of network is that DC power is difficult to interrupt, and commercially there aren't available circuit breaker operating with such a high voltages. And the second problem is what happens on the train, because they would need power electronics DC transformer to step down the voltages to values compatible with the traction packages. The opportunity is that compared to line frequency transformer, the power electronics transformer would have a better power to weight ratio, so lower power losses, as well as a better recuperation of the braking energy. So as well as a challenge, there is also an opportunity here. And so in this slide is actually explain how would work an MVDC traction power system, which will be fed at its supply node also by renewable. So in case of a high load, which is shown in here, so a lot of trains demanding power, the power will come from renewable, but will probably be not enough, so there will be a need of a top up from the main grid. But then this will only be the difference between what renewable can give and the need of the train. If there is a low load, so very likely all the power will come from renewables, and therefore the main grid will be only lightly load or no load at all. And if there is regenerative braking, so all the train are generating power back to the grid, and then also the renewable energy sources, they will inject power back to the grid. And then finally, this is a new kind of mode which is enabled by the medium voltage level of the traction power network, which then enable the export of power from one node to the other. So the rail electrification can also be used as a distribution network as well, which then would enable the balancing of the power across different nodes. These are examples of what are the potential converter for the traction power substation. One of them is the modular multi-level converter with full bridge module, as well the alternate arm converter represented in here. So both of them are topologies enabling the conversion, this high level of power and high level of voltages, as well as the blocking of the short circuit current. And similarly, these are candidate topologies for the power electronics DC transformer, which pretty much are similar to the topologies that I already showed you for the static frequency converter. The only difference is that they will operate as a DC to AC and AC to DC using this medium frequency transformer in here. But fundamentally, they will have a series input and a parallel output to step down the voltages. So these just simulations that we have developed to understand what is the efficiency of a 20 MVA modular converter. And as you can see, we are achieving an overall efficiency of around 98%, 98.1%, which is good, but is unfortunately still lower than the efficiency that we can achieve with a traction transformer, which is 99.9. So the advantage of using DC traction network is mainly because of the controllability, and the reduction of the transmission losses on the traction power line, but then in the substation itself, I will instead higher losses. So the case for using them, it is still not completely clear, and there is still a long way to go to improve the efficiency of converters. Talking about ancillary services and what the rail could do to help the development of the power system, I just wanted to present these other case studies where the traction power network can help to support the EV chargers normally fed by the public grid. So in this slide, it is presented the existing situation where the rail electrification is fed by the transmission network, and the EV chargers are connected to the public grid, typically at the DNO or DSO, distribution system operator level. The problem is when we add new charging stations, especially if we add a rapid charger having power of 50 kilowatt or more, there is a risk of a lack of capacity of the existing node. So sometimes it's fine to add this charger, sometimes there is a need of upgrading the line, which means more cables, more transformer, digging up the ground, and expensive work. And in some settings, for example, at railway station car parks or outside the railway station, for example, in taxi ranks, as well as bus station, there might be a possibility of avoiding this upgrade work and then connect directly the charger network to the rail electrification network. And this is what so some researchers are trying to do, and also us in Birmingham, we're trying to do by developing a new power converter interface, which is then taking power directly from the rail electrification and feeding the EV charging network, with the possibility also of integrating renewable sources, for example, on the canopies of the parking spaces, parking bays, as well as energy storage. They could help to keep the EV up and running, also if there is a significant load on the rail network, because this network will work only when there is spare capacity, which means there are no trains. And this is normally occurring because trains are passing by, and then there is some time before the next train will go on. So during that time, there is a window, an opportunity for using the rail traction network to feed the EVs. So the energy storage will just provide enough buffer for when the train is passing by, and keep this charging alive. So this is how the system will look like in case of an AC traction network. So the AC traction network has this traction transformer, single phase transformer, and is a single phase network. And then we have actually a number of possibilities, because chargers can be either single phase or three phase. And where typically the fast charger 7 kilowatt can be either, and the rapid charger, so 50 kilowatt or more, are typically three phase. So in principle, the single phase charger could be connected directly to the single phase traction network using step down transformers, which is then would help to reduce the power of the converter. The three-phase chargers are instead connected via these single phase to three-phase power converter. And then the battery is also connected on this charging network in here, as well as if present any renewable power sources. So this slide just showing you the prototype that we are developing in the lab at the University of Birmingham. And this will be done. So this is the single phase to three phase converter, as well as the charger. You can see that there is a huge potential for battery powered train to bridge the gap between electrified part of the network as well as running on branch line. And there is a lot of research on battery train, and the one that we have done here in Birmingham is to look at modular a traction drive using batteries, and where we have developed a modular converter. So this is a lab prototype with individual batteries on each of these sub-module feeding a traction train. The main advantage of a converter like this is the possibility of using the converter itself to balance the batteries. And this slide shows what happens to the balancing in comparison with a traditional system, where the cells are balanced in a time. So initially there is this big imbalance between the cells 1 and 8, and then after around 94 minutes, the cells are perfectly balanced. Compared to traditional systems, we can make the balancing faster by around 75% faster, because the balancing use a power circuit rather than a balancing circuit, typically low power. And during the balancing, these are zoom in waveforms taken at different times, where you can see the state of charge of the different cells. The line current of the motors and the line-to-line voltages are always balanced. So it is possible to achieve the balancing of the cells without any effect on the motor. And this is thanks to the usage of circulating currents. We have also compared the efficiencies of the this converter with a standard IGBT-based two-level inverter using a standard traction cycle. And it is possible to see the difference of the losses of these two converter. So the traditional converter will have mainly switching losses and smaller conduction losses, whereas the modular converter will have a very, very low switching losses and higher conduction losses. So overall, the efficiency of the converter for a traction cycle or a modular converter is actually better than the one of IGBTs, albeit the peak efficiency will be instead slightly lower. And in this slide here, we have compared the static converter efficiency, and as you can see, for the modular converter, which is this green line is actually slightly smaller than the efficiency of an inverter, traction inverter operated with a switching frequency of 2 kilohertz, but it would be slightly better than a converter, traditional converter operated with a switching frequency of 20 kilohertz. And when we talk about full load current, they will be almost comparable, as you can see. So we can then say that the modular converter with batteries are actually a quite good promising solution to balancing the battery cells, as well as having a battery systems which is better balanced and controlled compared to the existing solution. Then the last subject that I would like to discuss is the hydrogen power electrical multiple unit, because there is a lot of interest in using hydrogen as a replacement for diesel power. And the main advantage is connected to the possibility of a faster refueling, much faster than batteries. We have done quite a lot of work into hydrogen locomotives, and this is a train that's been developed at the University of Birmingham by a team of students. This is the hydrogen hero. And also the University of Birmingham has been actively involved into developing this for real through the Hydroflex project, which is the first hydrogen train which has been tested in mainline in the UK. In terms of research on fuel cell traction drives, we have worked on the modular multi-level converter with full bridges, and then we have studied a specific feature of this converter, which is the capability of boosting the input voltage on the DC side and boosting the AC voltage on the motor side. And this feature is particularly useful with fuel cell, as the voltage of the fuel cell decreases quite significantly with the load, and the full load voltage is around 20–30% smaller than the no load. So in traditional fuel cell traction drives, a boost DC-DC converter is typically needed. And we have then studied that by using this topology, we can remove the DC to DC converter. And these slides here shows some of the experimental results on the prototype, which is then showing the back boost capability. So the yellow curve is the DC input voltage, and the green one is the AC voltage across the motor, and this is a back operation. And on the one on the right, we instead have the boost operation, where the AC voltage is a peak higher than the DC voltage. And this slide here shows the boost characteristics and the comparison with the Boost VSI. So this is very similar to one of the Boost DC to DC converter, which is then showing a max boost voltage boost ratio of around 4.5 up to 5, depending on the duty cycle. And this table here then shows what are the sizes and the efficiency of the modular converter compared to a standard Boost VSI. I think here the most important thing is the energy storage, how it's changed, because in a standard Boost VSI we have a very small capacitors, but we have a quite big and massive inductor for the boost converter. In the boost modular converter, instead, the energy storage is switched. So we have much bigger capacitors in the sub module, but we can use a much smaller inductor. And the reason is because we have a multi-level waveform across the inductor that enables the significant reduction of the energy stored in the inductor. And that results in a significant mass saving, which is very critical for traction power systems. And the efficiency of full load is smaller compared to VSI, because we have more semiconductor and more conduction losses. But typically for traction, this is not a massive problems, and because weight is much more important. And this is also partially compensated by the fact that the waveform quality of the BMCI is much better. So we will have lower losses on the traction motor, which is then partially compensating for the lower voltage of the converter. So to sum up, we can say that the power grid in the future should evolve, and it should evolve not neglecting what happens to rail. And rail, they will need to have some new architecture of rail electrification systems which are more compatible with the grid, enabling power exchange with the grid in multiple points. And on the train side, we can say that while battery and hydrogen train are a suitable alternative to diesel, we need to develop further not only the rail electrification to enable the recharged battery, but also we need to have new type of converter with higher efficiency. So there is a need of obtaining a better integration of renewable for traction power systems, as well as reducing the power losses on board the trains. And possible solutions for that are given by multi-level or multi-source architectures, and potentially replacing some of the existing semiconductor devices with the new wide bandgap devices like silicon carbides. The only caveat to that is existing SiC. They have a 3.3 kilovolt max voltage and 1.5 kiloampere max current. So there is still a long way to go before this will be practically possible. Thank you very much.